Hello everyone. Good morning, good afternoon, good evening. Today we are going to learn Nexus Fabric Path architecture. So in this Nexus Fabric Path architecture, it combines the best of traditional layer 2 and layer 3 technologies, right? And which provides a new control plane as well as a data plane. Now this technology is mostly used in Nexus 700 and Nexus 5500 switches. So let's see how, what was the issue that was faced by traditional data center architecture, LAN architecture by, to overcome this fabric path architecture came into the picture. So first we will talk about the HTTP blocked port issue. So in traditional one, when we have a multiple redundant connection to two of the switches, so because of the multiple redundant connection and HTTP is working, most of the port will be blocked state. So even though if we have a multiple redundant connections, but we are not going to use all the connections. Why? Because HTTP has blocked it. So if we have a multiple connections, we cannot use it, and equal cost load balance path cannot be achieved. So this was the one, major issue. Second is the HTTP suboptimal path issue. So let's suppose we have a 3 switches and which is interconnected by cables. Because HTTP is working into the picture, so one port will be blocked state, even though I have a direct connections from switch A to switch B, right? But I cannot, host A cannot send the traffic from switch A to switch B. So what it will do, because of the HTTP has blocked this port, the host A will send a packet all through its third switch, and from there it will reach to switch B, and from there it will reach to host B. So this is called as a suboptimal path issue. Now to overcome this issue, we in the Nexus 700 or 500, Cisco implemented a technology we say as a VPC, virtual port channel, in which switch can be connected via port channel or via VPC by two peer switches, right? So all of the port will be in the forwarding state. No HTTP will, block port will be there. Port utilization, bandwidth utilization will be, happening at a port speed. But there was also one problem. So because of the VPC, we only have a limitation to connect two of the switches as a peer. So if we want to have third switches or a fourth switches like this, and if I want to connect it like this, it will not happen, right? So to overcome all these three scenarios, fabric path came into the picture, right? So what are the benefits of the fabric path? Benefits of fabric path, let me write it. So first, plug and play solution, right? Least configuration, third is provides equal cost multipath. Fourth, no HTTP issue. Or its troubleshooting. Okay. Fifth one, fabric path is scalable in nature. Right. So if I talk about the architecture, it will look like this. So these all are my, and this is my, and this I can connect it like this. So this is my spine switch. and this is my edge switch. And here I am running fabric path. Okay. Now let's see how, what is the architecture of the fabric path. So as soon as, we configure a fabric path into the switch, some processes starts, running on the supervisor engine, right? And some processes related to fabric path runs into the input output module, that is on the line cards. So, below is the fabric path architecture. So what happens as soon as we configure the fabric path, right, in a switch, DRAP protocol, which we say as a dynamic resource allocation protocol, dynamic resource allocation protocol. So this DRAP starts, providing a switch ID to each switches, and with the help of ISIS, they are shared between all the switches. So let's suppose I have a 3 switch. Let's understand with this example. So I am creating a very small topology, right? And I have, let's make it like this. Okay. Okay. So now as soon as I configure a fabric path, what DRAP will do, DRAP on each and every switch will allocate a switch ID. Let's suppose it's allocated 20, 30, 40, 50, right? And as soon as the switch ID is allocated by the DRAP, with the help of ISIS, these switch IDs are, shared between each of the switches, right? To identify that each switch must have a unique switch ID. So let's suppose if this switch got the, switch ID 10, which is overlapping of the first switch, then again the DRAP will allocate a new switch ID, right? So let's suppose now it allocated a 51 again, and then this switch ID will be shared between each of the switches to know the neighbor and to understand and to know that each switch will have a different switch ID. Now, once this switch ID is shared with the help of ISIS protocol, neighbor ISIS adjacency will be formed. And after that, a shortest path from each switch to other switch will be calculated. So from switch 10, what is the path, shortest path to reach switch 40? What is the shortest path to reach to the switch 50? What is the path to reach to 20? What is the path to reach to 30? So from each switches, a routing table will be created to reach each and every switches. I may not say a shortest path, all possible paths that are available from switch 10 to switch 40, 20, 50, 30, or from switch 20 to 10, 40, 50, and 30. All the routing table will be created and it will be shared to U2RIB. Right now, from the U2RIB, this supervisor will forward this routing information base to U2FIB. U2FIB is Unicast forwarding information base, and from the forwarding information base, the line card will finally save the switch ID routing table to the switch table. So switch table contains all possible route to reach each and every switch, right? Now the supervisor also have a L2FM, right, which saves or contains the MAC address of all end host. Now this MAC address of all end host, right, is sent to the MAC table of the line card, and this L2FM, we say it as a layer 2 forwarding manager. Okay. Now, once this happens, so each switch will have a switch table, second MAC table, right? So switch table, all routes to reach each switch ID, right? MAC table, all MAC address entry of end of point. Okay. Now let's understand what is the fabric path interfaces and fabric path switches. So there are two types of port, core port and edge port, right? So what is core port? Those interface which are a part of fabric path domain is called as a core port. So this is, let's suppose I have an example, this switch, this card is, let's suppose ETH 1 by 1, which is connected to fabric path domain. So this will called as a core port. Okay. And from this port only, my Ethernet frame will be encapsulated to fabric path frame. Okay. And what is the edge port? Edge port as those ports that are a part of a classical Ethernet domain, and it is used to forward Ethernet frames, right? And is called as a edge port. On this port, any classical Ethernet switch or host can be connected, and this port learns the MAC address. Those switch which are a part of edge port are called as a edge switch. So let's suppose if I make it more clear, right? This is switch 1, this is switch 2, this is switch 3. Let me change the color. And this is my fabric path, right? And this is my LAN. So this is called as edge port. This is called as a core port, right? This switch is called as an edge switch. And switch 1 and switch 2, they both called as a spine switch because it's all port are in fabric path domain only. Okay. So now understand, what is the fabric path frame architecture. So once from the edge switch, the traffic reaches, when the Ethernet frame reaches to the edge switch, and edge switch starts, forwarding it to the, from it edge port to core port, right, towards the fabric path domain, your Ethernet frame is encapsulated with fabric path header. Now under fabric path header, it is a 16 byte. Okay. Now the original Ethernet frame, which also contains the 801.1q tag, is encapsulated with 48-bit outer DA, 48-bit outer SA, and 32-bit FP tag. So this is your 48-bit, this is your 48-bit, and this is your FT tag. Now, if you talk about outer DA means outer destination address, which is the switch ID, sub switch ID, and the port ID will come into the picture when there will be a VPC plus scenario. If we don't have a VPC plus scenario, the value of the switch ID, sub switch ID will be 0. Likewise, the outer SA, the source switch ID, right? Outer source address, it will also have a switch ID, sub switch ID, port ID, like of outer DA, right? in the sub-switch ID and port ID will be used when we have a VPC plus into the picture. If we don't have a VPC plus into the picture, the sub-switch ID value will be 0. E-type will be 0x903, right, which says that, which indicates that this is not a Ethernet packet, but it is a fabric path packet. F tag contains, value 1 or 0, right? This tag is used for the unknown unicast and multicast or a broadcast type of traffic like ARP request or ARP reply, right? And TTL will be the 32. This is used to isolate or avoid the loops. Okay, now when it reaches to the 0, the packet is dropped. So TTL is used to avoid the loop in the fabric path domain. As any fabric path packet moves hop by hop, its value decrements by 1 from 32, and when it reaches to 0, the packet is dropped. Okay, so we will see the population of how the outer DA, outer SA and FP tag happens when we learn about the the traffic flow in the fabric path, which is in our next series. Okay, so thank you for watching Nexus Fabric Path Architecture. Thank you very much. Take care. Bye bye.